The concept of holographic time arises from the integration of two key theories, the holographic principle and insights from quantum mechanics and cosmology. Broadly speaking, holographic time attempts to rethink how time operates by suggesting that it, like spatial dimensions, could have properties that are fundamentally different from our everyday experience. Here's an in-depth look at holographic time, including its theoretical foundations, implications, and how it aligns with modern physics concepts. 1. The holographic principle, a foundation. The holographic principle suggests that all the information contained within a three-dimensional space can be represented on a two-dimensional boundary. This concept, originating in black hole physics, posits that the entirety of a black hole's contents can be described by information encoded on its two-dimensional event horizon. Historical roots. The holographic principle was first proposed by physicist Gerard, Hooft and later developed by Leonard Susskind in the 1990s. They suggested that the information in a volume of space is encoded on its boundary, similar to a hologram, which encodes a 3D image on a 2D surface. Implications for spacetime. This principle implies that spacetime itself might be a kind of hologram. In a broader cosmological sense, it suggests that the universe's information might be encoded on a boundary, giving rise to the notion that time, like space, could also be holographically encoded. 2. The intersection with time, holographic time. Applying the holographic principle to time requires a reinterpretation of time not as a linear progression of moments, but as a dimension that could potentially be encoded similarly to spatial dimensions. In this framework, holographic time suggests that time, like space, is not fundamental, but rather a projected manifestation of information encoded on a boundary. Time as information. In traditional physics, time is viewed as a continuous flow where past, present, and future are separate. The holographic perspective, however, suggests that time may be a property derived from the interactions and encoding of information rather than an absolute. Timelessness and quantum mechanics. In quantum mechanics, events do not unfold in a classical linear fashion. Instead, they exist in superpositions until observed. This aligns with the idea of holographic time, where time itself could be an emergent property rather than a fundamental one. 3. Holographic time and quantum gravity. One of the main goals in physics is to develop a unified theory of quantum gravity, which reconciles general relativity, the theory of gravity, and quantum mechanics. The concept of holographic time arises naturally in some models of quantum gravity, such as the ADS-CFT correspondence. ADS-CFT and time. The de Sitter a conformal field theory ADS-CFT correspondence, proposed by physicist Juan Maldacena in 1997, is a realization of the holographic principle. It describes a universe with gravity, in an de Sitter space, as being equivalent to a boundary universe without gravity. This correspondence implies that temporal dynamics in the bulk 3D space may correspond to processes on a 2D boundary, essentially creating a hologram of time. 4. The implications of holographic time. If time is indeed holographic, this would radically alter our understanding of reality. Here are some theoretical and philosophical implications. Non-locality. In a holographic universe, events may not be locally restricted. This means that temporal and spatial events might be interconnected in ways we don't fully understand, suggesting a non-local nature of time. Temporal entanglement. The concept of entanglement, where particles become linked and affect each other instantaneously, could apply to time. Just as particles can be entangled across space, moments in time could be interconnected, leading to phenomena like retrocausality, where future events could influence the past. Emergent time. In holographic theories, time as we know it is not fundamental, but emerges from more basic, timeless laws. This aligns with the Wheeler-DeWitt equation in quantum gravity, which predicts a timeless universe, suggesting that what we perceive as time is an emergent property arising from quantum states. 5. Philosophical perspectives on holographic time. From a philosophical perspective, holographic time challenges traditional notions of temporality, causality, and the flow of time. The block universe, in this model, all moments in time, past, present, and future, exist simultaneously within a four-dimensional block. Holographic time supports this view by proposing that our experience of time might be akin to viewing one slice of this block, where the full picture is encoded on a boundary. Free will and determinism. If time is holographically encoded, it could imply a predetermined or fixed structure to time. This might mean that our perception of free will is simply a perspective on encoded information rather than a causal choice in the traditional sense. 6. Challenges and criticisms of holographic time. The concept of holographic time is still highly speculative, and there are several scientific challenges. Testability. Holographic time theories often exist at the edge of testable science. Since they rely heavily on the existence of boundaries and information encodings that are difficult to measure, these ideas remain mostly theoretical. Interpretational complexity. The interpretation of holographic time relies on abstract mathematics and principles that are not intuitively relatable to human experiences of time. Translating these ideas into observable phenomena remains challenging. 7. Future research directions. Research on holographic time is ongoing, with some promising avenues that might make this concept more accessible and measurable in the future. Quantum computing and simulation. Quantum simulations may allow scientists to explore holographic time in controlled environments, potentially revealing insights into how time could emerge holographically in quantum systems. Cosmological observations. Certain properties of the universe's structure, such as cosmic background radiation patterns, might provide indirect evidence for holographic principles if they reveal boundary-like information constraints. Conclusion. The notion of holographic time remains a tantalizing theoretical frontier. By rethinking time as a holographic dimension, physicists can explore new ways of understanding reality that may eventually lead to a deeper unification of quantum mechanics and relativity. While challenging to validate experimentally, holographic time provides a framework to question and expand our comprehension of time, causality, and existence.